Hello everyone and welcome to Calculus 2. In this video we are going to look at an integration review, and that's going to prepare us to look at other integration techniques that we will see later in this course. So we're going to start off by reviewing chain rule or reverse chain rule, which is a U substitution. Let's say we're integrating cosine of 6 times x with respect to x, so there's my dx. We don't have a formula for integrating cosine of 6x, but we do have an integration formula for integrating cosine. And if you remember, when we integrate cosine, we're going to end up with sine of u. And don't forget the plus c, because this is an indefinite integral. So I like to teach this in a 5-step process. We're going to identify u. U is our inside function. In this case, it's 6 times x. Once you pick u, everything else is going to come out. The derivative of our u, our du, is 6, and we took that derivative with respect to x. So then we ask ourselves, do we have everything? We're calling this u. Notice that we're missing the 6 here. We can multiply it in as long as we compensate with a 1/6 somewhere in the problem. So what we're really doing is we're multiplying by 1. It's just a well-chosen one. And multiplying by 1 doesn't change the problem. So can multiply constants in as long as we compensate so that we're really multiplying by 1. So now we're going to do our rewrite step. So our rewrite step is going to say we're going to multiply 1/6 times the integral of the cosine of u, because we're doing a substitution here, du. Remember, all of this is du. And then when we integrate that using our formula, integrating cosine gives us sine. And then we're just going to substitute back in for u, because we want our answers in terms of x. And we know u is 6 times x. So our indefinite integral, our antiderivative, would be 1/6 sine of 6 times x plus c. Now, you can check your answers for any of these, and that's what's nice about integration. If I take the derivative of what I just found, and I'm going to put the plus c on here, but we know when we take the derivative of a constant, it's going to be 0. Taking this derivative is going to require a chain rule, and I'm not going to write that chain rule out. I'm just going to go ahead and do it. So it's going to be 1/6. Derivative of sine is cosine. And then we take the derivative of the angle, which is 6. And we know the derivative of a constant is 0. This 1/6 times this 6 reduces to just a 1. So I'm going to have cosine of 6 times x. And that is what I started with in the original problem. Let's look at another one. Let's say we want to integrate 2x over the square root of x squared plus 36. So this one's going to require a u substitution also. Now you may be tempted to look at the arcsine formula, but let's do a quick comparison here. If I integrate something that looks like this, du over square root a squared minus u squared, that's going to give us arcsine, but there's some issues with that, right? We don't exactly match this formula. Remember, in this case, u is my variable, so I have to have a negative in front of that u. I do not have a negative x squared here. And then if we try to do this formula, we'd also have to ask, well, what are we going to do with this extra x up here? So it doesn't really match that formula for that. So you could think about this like the preschool toys from when you were a kid. So you had this toy box and you had different shapes. You had circles, you had squares, you had stars, and you were trying to get all of your different shapes into the correct hole. So if this were a square and this is actually a star, that star is not going to fit in that square peg. So that's the wrong peg to use. So we have to figure out what else can we do. Well, what if we try to do a u substitution? Let's let u be that inside function, that stuff that's under that radical. And then let's take the derivative of that. The derivative of that u is going to be 2x, and we took that derivative with respect to x. So you can see that 2x is going to get absorbed in du, and that stuff under that radical would work as u. And now I've accounted for everything in the problem. So if I rewrite this, I'm going to have du over the square root of u. Because remember, all of this is my du, and that stuff under that radical is u. So I'm doing a u substitution here. And I could rewrite this. This is really u to the 1/2, which is really u to the negative 1/2 times du. And that we could use a power rule on. So when we integrate, we're going to add 1 to the exponent, and we're going to divide by the new exponent. Dividing by 1/2 is the same thing as multiplying by a 2. And then we're going to substitute back in. So I'm going to have 2 square root of x squared plus 36, and then plus c. There's my antiderivative. So there's that 5-step process for integration. Now we could check it, and I'm not going to check all the examples we do, but I'll check the first couple. Let's say we want to make sure that's right. Let's take the derivative of it. Now I'm not going to include that plus c. I could, but the derivative of that's going to be 0. Question is this derivative the same thing as what we started with? Well, we know we would need to rewrite it. So that square root's the same thing as a 1/2 power. And then we would keep the 2, bring the exponent down, subtract 1 from the exponent. 1/2 minus 1 is a negative 1/2, and then take the derivative of the inside. So you can see this 2 and this 1/2 is going to reduce to 1. So I'm going to have a 2x here over x squared plus 36 to the positive 1/2, because I brought that term down. And we know that 1/2 exponent is the same thing as a square root. So that's the same thing we started with up here. So we know that has to be the right answer. So let's look at some inverse trig functions now. So this was a u sub. That was one technique we talked about back in Calc 1. Let's say we want to integrate something that looks like this. 4 over x squared plus 9 dx. So when we think about our inverse trig formulas, we've got 3 that we can look at. Du over the square root of a squared minus u squared. That's your arc sine. We've got this one, du over a squared plus u squared equals 1 over a arctan u over a plus c. And then we have the arcsecant one, du over u square root u squared minus a squared equals 1 over a arcsecant absolute value of u over a plus c. So if we were looking at this, notice a u substitution wouldn't work here. If we tried to do a u substitution, maybe you would think about u being that denominator. So then du would be 2x dx. Notice we don't have an x. So going back to that analogy of that preschool toy, this is not the right shape for the hole that we're using. So we need a different shape. Well, this matches up with that arctan formula really nicely. We can actually think about pulling that 4 out. So that's equivalent to 1 over x squared plus 9 times dx. And then if we apply that formula, remember u here is my variable. So my x is really my u here, and a is whatever I'm squaring. So I'm going to keep that 4. This is going to be 1 over a, so this is going to be 1/3 arctan of u over a. And then we're going to have plus c, and I'm just going to simplify that. So this is going to be 4/3 arctan of x over 3 plus c. So let's look at another one. Let's say we have something that looks like this. We're trying to figure out how to integrate. Again, a u substitution is not going to work here, but notice that that's in our format for my arcsin formula. So let's use arcsin. So I'm going to copy these guys. Way I can paste them down here. Now, in this case, our a is not going to be a nice number. A is going to actually be square root of 5. Because if I take the square root of 5 and I square it, I'll get that a squared value back, that 5 back. So this is just straight application of the formula. This is going to be arcsin of x over square root of 5, and then plus c. Let's say we want to integrate x squared over the square root of 16 minus x to the 6. Your first thought may be a u substitution, and that's fine. Let's try it and let's see what happens. If u is that stuff under that radical, then du is going to be a minus 6x to the 5th dx. And notice we've got an x squared up here, not an x to the 5th. So that's a key to let you know that technique is not going to work. So let's try something else. Doesn't that look really similar to the arcsin stuff? What if we were to rewrite what's going on in here? What if we were to rewrite that as something squared? We know if we take x cubed and we square it, we'll get that x to the 6th. Let me clean that. And then let's do a u substitution. Let's let u be x cubed. The derivative of that is 3x squared dx. And now you can see that x squared is going to get absorbed inside of that du. We are missing the 3. We can multiply it in as long as we compensate with a 1/3. So all of this is my du. You put it down here also. Oops, I forgot the dx here. All of this is du. X cubed is my u. So when I do my rewrite step, 1/3 on the outside, this is going to be du on the top, and this is going to be the square root of 16 minus u squared in the denominator. So when I integrate, this is going to be arcsin of u over a. My a is going to be 4, and then plus c, and then we're just going to substitute back in. So it's 1/3 arcsin of x cubed over 4 plus c. So let's look at some other techniques. What if we had something that looked like this? So we've got a rational function. Notice the degree of the top and the degree of the bottom is the same. This is where we're going to use long division. So if the degree of the top is greater than or equal to the degree of the bottom, you're always going to want to use long division. And that's going to help us put this in proper form, and then we'll be able to see how we're going to integrate. So let's do some long division. We have x squared plus 9. We are dividing that into 4x squared. And we're missing the x term and the constant, so I'm just going to add those in. Plus 0x plus 0. That's the same thing as that 4x squared. So let's divide. X squared goes into 4x squared 4 times. And then we're going to subtract as we multiply. So 4 times x squared is 4x squared. 4 times 9 is a 36. Subtracting what we just multiplied through by gives us a negative 36. So division algorithm says I can rewrite this in terms of that quotient plus the remainder over the divisor. So that is equivalent to 4 minus 36 over x squared plus 9. And we're integrating with respect to x here. So I'm going to think about integrating each of those pieces separately, each of those terms separately. I'm going to factor that minus 36 out. So you see how I split that, integrating this term and then integrating that term. This guy integrates into 4x. This guy is going to be an arctan. So it's going to be 1 over a. In this case, my a is 3. Arctan of u over a, which is x over 3. And then we're going to have plus c. And then we're going to simplify that. 36 times 1/3 is a 12. So there's my final answer for that one. Let's look at another example. Let's say we want to integrate x plus 3 over square root of 4 minus x squared. It almost looks like a u substitution, right? We could think about that u being that denominator. So the derivative of that denominator is minus 2x. We're just missing that negative 2 in front of that. The question is, what am I going to do with this piece? This is a case where we want to split the numerator. Remember, we can split a numerator. You can never split a denominator. And when we split that numerator, you can see how we're going to end up using 2 different techniques to integrate this. So this guy will definitely be a u substitution. This one's not going to be a u substitution. Doesn't that look like our arcsine formula? So I'm going to rewrite this. This is going to require a u, and it's going to require a tweak. This guy does not, so you see how I split it into 2 different integrals? That's important. So think about your u substitution here. U is going to be 4 minus x squared. Du is minus 2x dx. So we need a negative 2 here, compensate with a negative 1/2 here. The reason we had to split this out, this guy doesn't need to be multiplied by negative 2. It can cause some algebra errors if you don't split that out. So when we rewrite this, I'm going to have negative 1/2 times the integral of, remember all of this is my du. All of that is my u. So I've got du over the square root of u. And we integrated something like that earlier. This is really u to the negative 1/2 du. And then when we integrate that, we're going to keep that negative 1/2. We are going to add 1 to the exponent, which makes that a positive 1/2. We're going to divide by that 1/2, which is the same thing as multiplying by 2, which is really going to reduce to just the negative square root of u plus c. And then when we substitute back in, it's going to be negative square root of 4 minus x squared plus c. So that was for that first piece. So there's that first integral. This guy's arc sine, no u substitution is required. We're going to keep the 3, and we're going to apply the arc sine formula. So this is going to be multiplied by arc sine of u over a. My u is just x over a, which is going to be 2, and then plus c. So what's my final answer? My final answer is going to be when I put these together. So when I put these together, I'm going to have negative square root of 4 minus x squared plus 3 arc sine of x over 2, and then I have a constant plus a constant, which is just another constant. Let's do another one. Let's say we want to integrate 34 over the square root of 8x minus x squared. This one is going to require completing the square because we want to see if we can rewrite this, excuse me, as an a squared minus u squared. Because if we can, then maybe this is going to be arc sine. So let's try it. I'm going to rewrite that as negative x squared plus 8x. To complete the square, remember you have to have a positive in front of that x squared. So that means I'm going to factor a negative out. That's going to leave me with a negative 8x here. And then to complete the square, we're going to take half the middle and square it. Half of negative 8 is negative 4. If I take negative 4 and square it, I'm going to get a positive 16. But this is really adding in a negative 16 to compensate. I got to add in a positive 16. Completing the square is really a fancy way of adding 0 to the problem. And if I add 0 to a problem, I do not change the problem. This factors into x minus 4 times x minus 4, which is x minus 4 squared. So you can see how we're going to get 16 minus x minus 4 quantity squared. If I were to multiply all this stuff out, it would be equivalent to negative x squared plus 8x. So let's do a rewrite here. I'm going to pull that 34 out. This is the square root of 16 minus x minus 4 quantity squared. And we're going to do a u substitution. U is going to be that x minus 4. Du is 1 dx. So you can see how we've got du up here, and this guy is u. So when we do our rewrite, we're going to have that 34 that we pulled out. All that in the numerator is really just du. And this is going to be over the square root of a 16 minus u squared. So when we integrate, oops, this is going to be arc sine of u over a plus c. And then when we sub back in, we have 34 arc sine. Remember, u was x minus 4. So 34 arc sine, x minus 4, all over 4 plus c. Final answer. Let's look at another one. Let's say we want to integrate something like this. What could we do? We could try u substitution. Let's see if u is equal to 1 plus e to the x. Then what would du be? Well, du would be e to the x. So notice we're missing an e to the x up here. What if we use that same concept and we add 0 in this case? So what if I add an e to the x and I subtract e to the x? Is that a legal move? Let's see what happens. So I'm going to have 1 plus e to the x. I'm going to split the numerator here too. Over 1 plus e to the x. And I'm going to have minus e to the x over 1 plus e to the x. So that's the same thing that I had here when I added that 0. I just added 0 in a really clever way. And this first fraction is going to reduce to 1. And then we're going to have minus e to the x over 1 plus e to the x. So this is going to be 1 dx minus the integral of e to the x over 1 plus e to the x dx. Now you can see where that u substitution is going to come in here, and that first term reduced to 1, which is going to be really easy for us to integrate. So I'm going to move this guy over here. So let's integrate. We're integrating in two pieces, right? Because we've got two different integrals we're dealing with. Integrating one, we're just going to get x plus some constant. When I integrate this using a u sub, I would now do my rewrite. Don't forget the dx there. So this is going to be integrating du over u, and that is ln of absolute value of u. And when we substitute back in, we're going to have ln of the absolute value of 1 plus e to the x plus c. Now, in this case, 1 plus e to the x is always going to be positive. So that's the same thing as using a parentheses there. The absolute value is not necessary on that one. So what is our final answer? The final answer is going to happen when we put these two together. So we're going to have x plus c minus, because that minus came here when we separated the numerator, split the fraction, ln of 1 plus e to the x plus some other constant. Now, these are not necessarily the same number. We could call this constant 1 and constant 2. So, final answer, if I clean that up, if I take a constant and I subtract another constant, I'm still going to have some kind of constant. I don't know what it is. We don't have an initial value, so we would just call it plus c.